So the first thing I want to do before we go any further is number 2. I want to say about number 2B because okay. Until somebody asked me about that, I didn't realize that was on there. Let's one thing. So hint on number 4, question 2B. So let's say we have an operator here. And permission operator. If this is an eigenfunction about what does it mean?
We have the eigenfunction and eigenvalue.
We get our eigenvalue here. And we get our eigenfunction back. And what do you know about a permission operator? What are the 3 properties for permission operator?
Eigenvalues are real.
Eigenvalues are real. Put into details.
The integral from minus infinity to infinity of the normalized.
They don't have to be normalized, so true going down.
Oh, yes, for
Phi j star, phi I star, I mean phi I, dx
is equal to 1. No, 0.
0. The I doesn't equal j. You call that, that's what we're talking about. Okay. What's the next property?
On a basis.
The eigenfunctions form a basis. So what does that mean here? That means that the psi here, I could write any wave function if I wanted to, as the sum on n, a n, phi n. Does that make sense? Now, what I want to convince you of is it turns out that if you take this a n here, you take the modulus of it, meaning modulus squared, that's going to be the probability that when you measure the system, it's going to collapse into a state. Okay. So let's just go. I'm going to set this up for you. So let's talk about something else. One of our postulates said what? If I measure the psi here, what does it do? Collapse into
What are the eigenfunctions?
what are the eigenfunctions of what we're measuring? So this is my generic wave function. If I go to measure O on this system here, this wave function is going to collapse into a particular one of the eigenfunctions. The question is, what probability is that likely to happen? What I want to convince you of is that when, we will see that if psi is measured, probability that psi collapses into a particular eigenfunction. Let's say J. Okay, is AJ squared. That's your probability.
Is this just for permission operators?
Oh, this is all just for permission operators. This is not true at all. Because you don't have this class to believe in. Like that. So what I want to do is give you a proof of this. Proof. Okay. What should that wave function here be? Psi. That psi should be
Linear computation.
in the broad sense. We want our wave functions to be normalized. Okay. So what we want this right here. Let's actually calculate this. We have this guy here. There's actually there's going to be a life lesson in this. Here's our life lesson. Okay, I'm going to take psi. I'm going to put it in the cell here. So here's my psi. I want to place here psi star. How do you have to write it?
the sum
Here's the sum.
from A, like sum from N up AN
A-N,
times I star.
5 star, it'd be the star, and then. Now tell me why that's wrong. I mean, this is a very common thing. This is why it's a life lesson, right? This basically, it comes in times itself, and I know that this is psi. So that's psi star, done.
No,
Yes.
it's wrong. It's because A is real.
A doesn't have to be real. Okay, often they are, but it doesn't have to be.
Even if you just like the whole thing, I mean, the normalized thing is just A, like the sum from N of AN squared.
So there's a problem right here. Yep.
This is most of the functions are just going to be zero.
Yes, but the problem here is what would a mathematician call this variable, this index here, n? In other words, suppose I put an R, can I put an R here? Yeah. How about an L? It doesn't matter what I call it. Okay? When it doesn't matter what you call the index, what do you call that then? You call it a dummy index. Okay. So the fact that I can make this anything I want it to be, that's called a dummy index. And if you're squaring it here, this dummy index on this from here is not going to be the same dummy index on this from here. Because what's going to happen if you have it like this, you're going to be missing cross terms. Okay. So what you have to do is you have to make this a different index. So I'm going to make this m's. Yeah. And let me give you a hint on this. Just so you can see what I'm doing now. So if you write this, you this cross terms. In other words, if I had that, what would I do? I could pull out these two sums here. And this would be AN star, AN, phi n star, phi n. That's all I have. Now that's ultimately what we're going to get in, but you have to be careful here. When you really multiply this out, what would you have?
A bunch of zero.
Well, when you do the integral, you get those ones, okay? But I'd have cases like these here are all the same. When I multiply this one by this one, are they really all the, are we only getting somewhere? Are we only getting terms which have the same index?
Yeah.
No. Let me just give you a simple example. Let's say we have psi is this. Let's say it's just say A1, phi 1. Let's say A2, phi 2. Let's just take something simple like that. So if I were to say, this is just a sum going from I equals 1, let's say n equals to n going to 1 to 2 of AN star phi n star times this. That's just a still on n, AN star, AN, phi n star, phi n. And how many terms would there be there? Just the A1 star, A1, phi 1 star, phi 1, the A2 star, A2, phi 2 star, phi 2. But if I actually multiply this by this complex conjugate, what do I also have? A1 star, A2. I have the cross terms, right? So this does not have. So the life lesson is whenever you have a term that has a sum in it, and you square it or cube it or do any other power, when you write those other terms in the sum, you always have to change the index. Otherwise, you'll be missing all the cross terms. You have to, just so you know, you have to make that mistake a couple of times in life before you stop. Everyone makes that mistake and then you keep complete garbage, and when it was me, I go, oh. Didn't change my inputs. Okay, that makes sense?
This is just the, like, all the combinations.
Yeah, because what you would have in this case here. So in reality, we would have. Right, if I put this in here, I'd have A1 star by 1 star. A2 star by 2 star. Times A1 by 1. Plus A2 by 2. So I have plus times this, that's great. This guy here. Then I have this times this, that's fantastic. But then I also have this times this. This. So you'd be missing all the cross terms. Okay. Makes sense. So let's go through and do it correctly. Then you're going to see the power of orthogonality and the Kronecker delta. So let's go back and go here. And we're going to put in basically now we're double sum there, written properly. We're going to have to just pick the complex times of both terms. This gets multiplied by sum of n, an by n dx. So I can pull the sums out of the integral. And I'll pull out the a's as well. What am I left? Just so you know, sometimes you can't pull sums out of integrals. That to me are the problems that you don't do because you can't pull the sums out of the integrals. So you'll have the mathematicians deal with those. That's where I start losing patience with math. It's just like, no, those sums are coming out of the integral. I'm not, no. Yeah, that. Now, here's the beauty of this. You know exactly what this has to be and why. That's true.
I agree with Jay.
Yep.
0 when they're not, 1 when they are.
Everyone agree? If these are not the same, we have 0 because they're orthogonal. If these are the same, we're assuming that the eigenfunctions are normalized to a 1. Hey, do we have any nice, cute way of writing things that are either 0 or 1? All right, buddy. The Kronecker delta. So we're going to see what Kronecker delta is, why they're really nice. So this becomes my sum on an star an Kronecker mn. Okay. What does that reduce to? If n does not equal n, we get a 0. If m equals n, we get 1. So what that means here is that this whole thing here reduces to a sum, either on n or on m. It doesn't matter which way we write it. Okay. An star, an. So Kronecker deltas kill sums. That makes sense. So kind of getting used to kind of writing this formally, that ends up becoming really more sophisticated the work you do.
How does that prove that?
We ain't done. Okay. Now, what do we know? This equals is normalized. One. Okay. So we have here, it's this guy here. Has to equal one because it's normalized. So that also equals our buddy. So, how do we interpret this? Well, all these, in other words, this is saying this plus this plus this. All these here up to, let's say, the last one ever, they all had to add together to equal one. So we need some interpretation here.
There's some of the normalized, the sum of the normalized, is it the eigen function?
What else adds together to what else equals one, right? How do we interpret these size?
Like the probabilities?
They're probabilities. Okay. Well, so what happens if you add up the probabilities for anything?
You go to one.
If you add up the probabilities for something to happen, they always have to add together to equal one. These are all adding together to equal one. So how are we going to interpret this? This value is going to be that if we measure that wave function, this is going to be the probability that that wave function collapses into that first second function. So this right here is a probability for it to collapse into the first state. This is your probability for it to collapse into the second state, third, fourth, and fifth. Yeah. So the larger these numbers are in front of something, the more likely you are to have that wave function collapse into that state. Pretty slim. So if I had to say like this, so let's say I had a psi here, and I'm just going to make some here. Let's say I have a quarter. No. Quarter. That's really what I have. 5(1) plus square root of 3 over 2 by 2. Let's say I have that. What is the probability that this state is going to collapse into phi2? And if I measure this, it can either collapse into phi1 or phi2. What would be the probability that it's going to collapse into the phi2 state?
It would be the 75%.
Frequently called. I agree with that. Okay. It's going to be this coefficient here squared. The probability for it to collapse into this state is going to be the modulus of this. Probability that it collapses into phi1 is equal. What would happen if I had an eye? What happened if I had an eye there?
It's,
Sure.
oh yeah, no, because we take the complex unit. Yeah.
Yeah, you'd be getting this. Well, what is the modulus? Something
The
mean?
complex conjugate times the complex.
Yeah, this would be minus I over 2 times I over 2. Minus I times I is 1. So this is to be 1 over 2. Okay, I'm doing real quantum mechanics. I'm not giving you the baby stuff that's your normally doesn't matter. I'm giving you the real full quantum stuff. Okay. So that's said. Let's go on in our discussion with fermions and bosons. So we talked about spin, baryons. So we decided to view particles as basically spinning little balls like this. And what does this little arrow here represent? If you have a spinning a little ball like that, what does that arrow represent? Angular momentum of the particle. So this is right here. Normally we would call this would be the L of L is angular momentum. But we never use L for angular momentum of a particle. We always call that S for the spin. Okay? So we call this S. And you can show, well, not in this course. Okay. You can show that the magnitude of this S is equal to H bar square root this little script S times S plus 1. And this little S here is called your spin quantity. Okay. And you can show that what kind of little S's do you get in nature?
Whole numbers like one, two,
Integers?
integers or half of the integers.
Half integers. Okay, so in nature, S is either an integer or a half. So if we have integer S, 0, 1, 2, 3. This
You could just plug it in.
you have, what do you call them? These are the bosons. So give me some good bosons in life. No, that's gonna be a ferrium. Okay. Photon. Photons have S equal 1. Okay. Those of you who know a little bit of particle physics. W plus and minus particles. These have S equal 1. This is in particle physics. Okay. Another particle in particle physics. G's, these are particle physics. These have S equal 1. Gluons, also from particle physics. These have S equal 1. Okay. Gravitons, assuming they exist, would have S equal 2. Let's make it a little more down to earth. Helium-4. Right, this one I always have to look at. It's either 0 or 1. I think it's 0, but it might be 1. How's that for a useful statement? It's either 0 or 1. You know, that's. But the main thing is that this is an integer. That's going to become really important for us. We'll come back and look at this. So helium-4. It's going to be an example of bosons. These are all bosons. There's a whole lot more. But these are some of the main ones. Okay. Now let's look at the half integers. So these are half, 3 halves, 5 halves. This. Examples of these would be quarks. Okay, quarks have S equal. What's the classic case of an S equal half particle? Electron. The electron. That's equal half. Neutrinos. Well, muons are. I'm gonna put these in a big broad family here. I'll put these over here. We'll call them muons. That's equal half. The muons basically have the electron. What's an even heavier electron called? A tau. What else? Protons and neutrons, okay? So protons. Please, that's equal to neutrons. That's equal to.
Isn't it proton and neutron is made of quarks?
Correct.
Why are we considering them as you're not elemental particles?
They're not elementary, okay, but they're still fermions.
Okay. So a combination of fermion, the combination of particles that are fermion will be a fermion.
No. Okay. Not necessarily.
So I think
I'm going to talk about what a meson is, because a meson will actually be a boson. We don't know that yet. Okay, so these are what they have. Now, wasn't you could say, well, okay, fine, classified spin, who cares? This is why we care. It turns out that the statistical mechanics, which ultimately goes into thermodynamics, is very fundamentally different from these two objects here. Okay, all fermions obey the Pauli exclusion principle. Fermions obey the Pauli exclusion. Bosons do. So, before I go into what this is, well, let's go into it right now. What does the Pauli exclusion principle say? We have to be more fussy now. Okay. No two identical fermions, meaning what does it mean to be identical? You'd have 2 or 3 or 4 electrons, or 2 or 3 or 4, 12 protons. You have to have identical, you have to be dealing with the same particle. Okay, it's not an electron in a proton. No, you have to be dealing with a group of the same particle. And if you have a group of the same particle, no 2 of those identical fermions can have the same set of quantum numbers. There's a better way to word it, but I'm not going to do that. Okay. So the Pauli exclusion. And I'm just going to call this PEP for this. This states that no 2 identical fermions same set quantum. So I want to say a little bit more about the spin. One other thing, again, something I'm not going to prove, but the result is easy. Again, when I do particle physics, if you want to see it there, I take my course in particle physics, and I'll show you exactly why it's the case. It's actually quite beautiful. Let's go back to spin. There is another quantum number associated with the spin quantum number. This is what it is. I'll show a little picture. So here's our particle. Here's our little vector spin. What can you always do with vectors? You can break it into components. So what I'm going to do is I'm going to look at the z component of this. So this is the z component. Okay. It can be shown that this S of z is equal to m sub s times h bar.
what is M sub S?
That's what we're going to do right now. Where m sub s could be a half. I mean, it could be s minus 1, s minus 2, all the way down
S minus
to minus s. This M sub s is often given a lot of different names. It's sometimes called the azimuthal spin quantum number, sometimes the magnetic spin quantum number. There's a lot of different names it can be. I'm just going to call it M sub s. Okay. So I'm going to give you some examples, and then you're going to see you're actually used to that quantum number. You just haven't thought about it. So let's see what we have. Let's see a good example. Let's take an electron. Hey, what is S for an electron? So according to our little rule here, what are the possible M sub s values?
1/2 minus 1, 1/2 minus 2. So
We sort of ask, we keep on subtracting 1 till we get to
-1/2.
minus s. So let's start off with this. Let's subtract 1. What do we have? And so we stop. So now let's draw a little picture of this. What would this be? Well, this would be the particle like this, S here. This would be an M sub s value of what's the half eight? Here's the M sub s. This is given a name. What do we call an electron like that? We say it is a spin up electron, because it's a positive component. So this is what we mean by a spin up. Hey, let's put in this crazy value over here called minus a half. Let's see what we get there. Get down. And if it just as well spin this way, then I can look at this one. All right, so this magnitude here and this magnitude here, this doesn't change magnitude here. Okay. This would be minus a half. Here's my M sub s. Hey, does this one have a better name? That's our spin down electron.
How does the spin affect the overall power?
It's just the electron has to have an s equal.
Yeah, no. Okay. But like, how does a spin up or spin down affect the particle? What is it?
It depends on the system. I mean, right now, this is just, you could have this, or you could have this. This is just any way it could be. It can only be like this, be like that.
The point is, no, my question is like, why do we care where or not it's a spin up or down?
We're going to go to the problem and we'll see how good this is. Okay. Yes.
How do you tell which is up and down? Is this just based on what coordinate system you're using?
Well, what you do is normally when the z-axis, anything going up, and the z-axis you go up, and anything going down. Right. So this is positive, so you call up. Down, so you call negative. What would happen if we had the following? Let's say we had a particle. It had s equals 5s.
Yep. Is it a problem that like they're not spinning in opposite directions? Like they're like the spins aren't 180 degrees from each other?
Yeah, they can't be like that. They fundamentally cannot be like this. When you draw the pictures, you draw this and you draw this. But they are not that at all. What do you mean? They can't be that. You can't have a spin like this and you can't have a spin like this. It's always like this. Okay, or anything like this. There's a technical problem I'm not going into. Well, let me actually want to pull that. I said so. When can you measure two things? Only when the operators when they commute. Remember, I did this little proof that showed that if your operators commute, you can actually measure them at the same time. Now, so what would happen? You'd have a spin you'd have an operator connected with the component of the spin, but you would also have operators connected with the x and the y components. What do you think those components don't do with each other? They don't commute, which means you're only allowed to know one of the components at a time. And by convention, it's always the z-axis. So if this were going straight up, the x and the y components of the spin would be 0, and you'd only have the z component. Then you'd have all the components known at the same time, and that's not possible. Okay, you can only you have to draw like that. That's a slope.
I mean, it can't be on any dioxide.
Well, so often if you look at books, you'll see pictures like this. Meaning that this arrow here can be anywhere along this circle. In other words, let's say my hand here is the spin vector, that this is your S anchor, it can be anywhere along here like that. So anywhere here along like that, you have the same value of zero.
Is like the theta knowable?
Does the theta would be fixed because you know this side here, you have this side here, so you can get that. It doesn't help you, but you can get it. Okay. Again, I haven't gone into really the commuting operators a lot. When you take the course in quantum, I hope you all do. Then you'll spend a long time talking about operators commuting. There's a whole thing you'll get. So I should put for a while. Okay. Tell me about the M's best values then. What would they be? 5 half.
Minus 3 half.
3 halves?
1 half.
1 half. 5 half.
Negative.
Minus 3.
And
Stops at minus 1. So what are those pictures? If I would say draw the picture here for these, what would you do? Well, you have this fellow here. I have this being 5 halves H bar. That's my SMC. I can just as well have this one, so I can have this one here. This would be my 3 halves C. 3 halves H bar. I have this one. That would be my half H bar. Then I can have this one here. That'd be my minus half H bar. I can have this one here. That'd be my minus 3 halves H bar. I can have this one here. That'd be my minus 5 halves H bar. What are the M's and best values for a photon? I gave it to you already. Photon. So what are the M's and best values?
1 0 max.
1 0 minus. What on earth does it mean to have 0 Z component of the angular momentum?
You don't on the polar.
You can't go. Okay. This S is equal to 1. The spin is always there.
Not spinning.
Your Z component of the axis.
Okay, so this would be the 1. This would be minus 1. Where's 0?
Oh, it's
It's right here.
So
Well,
then I was going to say the angle is 0.
it'd be in the XY plane. It actually precise. Yeah. It doesn't have to precise. You don't know what it is. Okay.
So that must mean that for bosons, operators can be.
Well, no, you would have this here, but you don't know what the X and Y are values because it could be anywhere along this plane. So because you have your Z, the Z component, because it's 0. But is that if here's my S for the photon, where is it along? You don't know that. Okay. Now, how does this all apply to all this up here? It turns out it doesn't, but I had nothing else to talk about today. So this is how it connects to things here. So let's go back to our electron. So did we have 9 or 10? How many electrons did we have in that 1D box? 10 electrons in a 1D box. So let's ask, what is the ground state energy? For 10 non-interacting electrons in a 1D box. Let's call it the energy level. How does our 1D box look like? We have n equals 1 here. N equals 2 here. Where's 3 go? A lot higher. Remember, because this is E1. This is going to be E2, which is 4E1. You're going to have something a lot higher, 9E1. And okay, I can't keep the spacing going the same row because it's going to go weird. So I'm going to put the 4 and the 5 here. But that would actually be a lot higher. So it's spacing increases. Okay, so I take one little electron, I throw it in my little 1D box. What's the lowest it can go? It can fall all the way down here. And I'm going to draw this like this. Okay, so what would be all the quantum numbers for my little particle? I'm in an n equals 1 state. The s equals half. Can I change my s equal half value? No, that value is assigned by God. You can't change it. You pick up a particle, you flip it over, it says electron, s equals a half, God. You can't change the s value for that particle. It is fixed. Okay, so this value right here, this is n equals 1, s equals a half, and
it's always going to fill up.
well, it may or may not. It's usually goes up. With this, without knowing certain things here, it could go either up or down. Okay. And then this would have an m sub s value of a half. Now, where does our next? Because the way I've drawn it like this is to spin up. Now, where does our next electron have to go? It can go all the way down here, but how does it have to go? Tell me why we can't have this. That is not allowed. Because then these would both have the same quantum numbers. Okay, and they are fermions, and fermions are not allowed to have the same set of quantum numbers. So you have to have this combination here. Right? So the n is the same. The s can't change. But now the m sub s can change. This is going to be minus a half. Well, the problem with chemistry, there's not a problem with chemistry. But part of the problem with chemistry, which sounds like I've just contradicted myself, is the fact that you get away from that class and you think that the Pauli exclusion principle is only something that electrons obey. It's actually far more broad than that.
Any energy level is forced to be occupied by 2 electrons?
Okay, it depends on, and we're dealing with this 1D box.
Oh, okay.
When you use something else, you're going to have a more complicated structure. Okay, where's our third electron have to go? Yeah, it's going to go as far as it can. It cannot go down here. How come?
It's full.
Yeah, basically, it either have to be up or down. Either way, that's not allowed. So this has to go here. Okay, so the next one, down, and then so on and so forth. Why would that be the ground state for this system?
Oh, you'll be. It's the lowest energy.
It's the lowest we can put all the time particles. Yep.
This is only the case when there's like 2 values for s.
Okay, we're going to go into what happened with the bypass. Okay, so what would be then the energy of my system? Yeah. So what would you have? You would have. The E ground state for the system. Okay, so what would be the energy connected here? Each electron would have E1. E1. So this would be 2E1.
And factorial squared.
No. This is going to be. So this is going to be 2E2. The E2 is 41. 41. Okay. Again, it sounds like you have a list for a speech impediment when you say that, but that's just the way it is. It's fine. This one. So this would be 3E3. That won't be that at all. It'll be 2E3 plus 2E4. That's 3.
Is it
the electrons, because you have 2 protons. Okay. So what does this become? This becomes 2e1. This would be 2 times 4e1. Plus 2 times 9e1. It's 2 times 16. Plus 2 times 25. And then you add these all together, so you get some number. What?
Believe it's 106.
106. That makes sense. What would be the energy of the first excited state? And what would it look like? Try to say draw, what would they have?
So that you want to somewhere.
Okay, so if I have my little picture here, and here's my n equals 1, 2, 3, 4, 5, 6. Here's my states. These are still the same. So what has to happen here? One of these particles here has to go to first excited state. The sixth state. Like that. That's what the first excited state would look like. Then what would be the energy then for this?
Well, everything the same, but E5.
So you'd have 2e1 plus 2e2 plus 2e3 plus 3e4 plus
1
e5
plus 6
plus e6. That's what you would have. Okay. Now, what would happen if instead I put in 10 non-interacting half particles? How many particles can go in the n equals 1 state? How many MSS are there for this? For the S equals 5 half? There are 6. So how many particles can go in the low state? 6. So I can have 6 particles here. Why am I not drawing spin up and spin? Why am I not doing this? That only works for the S equal half. So how many particles they have to go up from here?
4.
4. Because we have 4. So the energy of the state would be what? The energy of the ground state would be 61. It's 42. What about the first excited state?
It will be 61 plus 33 plus 1, 3.
Now we have to go think.
Can't you also do 5e1?
Yeah, so there's a couple of options here. The question is, which is the low state? Is that we're going to take one of the particles here to get up here? Possibility. Or, since it only has 4 now, I can take one of the particles here to get up into here. The question is, which one is cost lower, has the lower energy?
The second option.
Yeah, this is going from basically, remember that this is E1, this is 4E1, this is 9E1, like that. So this is only going to cause me to have, I have to put in basically 4E1 units of energy to get this up here. Because to go from here to here, it's going to cost me 5 units of energy difference. So it's going to cost. That makes sense? Now, what happens, let me do one more thing that will calculate. What happens if I have 10 S equals 0 particles?
S equals 0.
Repeat. or 10. S equals 0.
It would all be the same.
Yeah, they can all go to the ground state because S equals 0, you are a boson, and what you do not obey. The Pauli exclusion principle. In that case here, I can have all 10 of my particles here. So here the energy of the ground state is 10A1. I'll just leave you with this idea. What does it mean to be a superfluid? What are superfluids? They are fluids that flow with 0 viscosity. There's only one naturally occurring one in nature. And what is it? Helium-4. Okay. So what do we say helium-4 is? Helium-4 is a boson. So I can take a gas of helium-4, I can cool it, condense it to a liquid, keep on cooling it, and what will eventually all those particles do? All those helium-4 particles could then collapse into the ground state. Now, what causes viscosity? You somehow are losing energy. Right? It's some kind of an internal friction. If you are in the ground state, how much energy can you lose? None, because you're in the ground state. There's nothing to give up. Okay. So if you were to actually take all the helium, pull it low enough, and dump them all in here, what would happen here? This is going to flow without any viscosity. So helium-4 is an example of a super. It's only naturally occurring. If you had helium-3, helium-3 has, I think it's not C class. So this would be an example of a fermion. You can't make a superfluid out of helium-3. You can out of helium-4, but not out of helium-3. One of my professors in grad school, he did the calculations on this. He got the Nobel Prize for it. Well, have a good day. Sorry for going a little late. Yes.
Yeah, it's 13.6 easily over. That's a, is it a classical? Like,
No, that's actually that's the bottom result.
Oh. Okay. Oh, okay. Because I remember when we were doing that, we were doing like.
Well, we did the boron.
Oh, and then we.
So much less.
Yeah.
And then it turns out that that's actually the real actually work correctly. Yeah, exactly.
Oh, really cool.
I'm going to the office.
I'm not.
I'm going to house.
Actually, yes, I am.
Thank you.
Basically just cut in, you fix it for example. Yeah, gotcha. Then you cut it, and then you go and you mount it. Mount it in boxes.
Okay.
Don't forget to. You're not the right guy. What?
You're not the right guy. Oh, yeah, Dr. King?
Yeah, I know. He was telling me, oh, how are you gonna get to? He was telling me how you gonna get, yeah, he was telling me how I'm gonna get to the airport. I was like, yeah, then.
What?
Yeah.
That's crazy.
That's crazy. Oh, the live me, but hey, that's next time.
No.
I'll take you, but you gotta pay me.
Actually, it's oh, no. Yeah. It's already been.